Welcome everyone. Today's lesson is entitled Relations and Functions. This is very much a foundational lesson in that we'll explore the concept of a function, go over some of the notation behind it, and then some of the manipulations of functions both with equations and with graphs. So why don't we go ahead and dive right in here. At the top, just a couple things to fill out as we begin the process. So the first thing I see on my sheet, and you should see it on yours, is just sort of what is a relation, and then what does it mean to be a function. So let's distinguish the two here. So first and foremost, I've got a relation is really just any set of ordered pairs. That's pretty much what it comes down to. So if you can go ahead and jot that in. And so what I think of it is, it's just a relationship between any two variable quantities. All right, very good. Now, getting into really the crux of the entire lesson, what does it mean then to be a function? And I would argue that a function really is just a subset of a relation, meaning it is a specific type of relation that, that we're going to be looking at over the course of the lesson here. So when I start to think, all right, from relation to function, here's what I would go ahead and say. So same idea, it is a relationship between two variable quantities. Now here's where we want to be a little careful though. It's a relationship where one variable quantity depends, and I'm going to have you underline this, so it depends on a second variable quantity. So we talk about that a lot when dealing with functions. If something is a function of another variable, then it depends on that variable. So let me just make sure I have this correct for you. A relationship where one variable quantity depends on a second variable quantity. Okay, and we'll see what that means conceptually here in just a couple minutes with a good investigation. And then here's what I would say mathematically, or really algebraically, and you've worked with functions before, and I'll bet you this is probably the most basic way your prior math teacher talked about it. Mathematically speaking, we cannot have a repeat of the x value, so please do make sure you put this piece in. And the way I like to phrase it as, each x can produce only one y. Okay, there we go. All right. So when I look at a set of ordered pairs, the most basic way to think about it is I cannot have a repeat of the x values. Each x can only make one y. And we'll talk about inputs and outputs and how that plays out here, but that'll take just a little time to develop. So you have your two little definitions here. Again, a function really is a type of relation, and let's go ahead and explore that in a little more detail. So, investigation one. Each set of ordered pairs represents a relation, and the question is it a function? Now, one of these, I'm looking at letter A here, is a little contrived, but it does kind of really emphasize what I'm getting after. And then letter B is a good one. I kind of just looked up this data recently and put that in. So let's go ahead and look at letter A, answer the questions related to the definition up here, and kind of move forward from there. So first of all, it looks like 10 students SAT scores, math as the first value, and then verbal as the second value. So I guess arguing it, well, you can tell me what you think, but I'll pose the question, does the verbal score depend on the math score? So if you look at like this value right here, does this 600 have any correspondence to that 520 right here? Did this number depend on that number? Did this 500 depend on that 580, et cetera, et cetera? And I think you'd probably agree with me that no, certainly the verbal score does not depend on the math score. They are independent of one another. And so conceptually speaking, we would say, well then is the verbal score a function of the math score? No, absolutely not, because one does not depend on the other. Now, let's take the context out of it for just a second and just look at the 10 ordered pairs that you see right here. And if I just gave you those 10 ordered pairs with no context whatsoever, you would still mathematically say that it does not represent a function because in this particular case, I have a repeat of the x values. So this 580 right here cannot produce two different y values. So that's what I wrote right here, no repeat of x's. Each x can produce only one y. So this 580 can't produce both a 500 and a 540 in terms of it being a function. Okay, and I know you're saying, well, what would happen if we were doing the same thing and we didn't have a repeat of the x's? Well, conceptually, we would still say it's not a function. Mathematically, it may be, though. Again, but I just want to be clear in terms of a set of ordered pairs, each x can produce only one y. And so this 580 right here cannot produce more than one y value. Okay, very good. Now, letter B. So just got this data here, ACT scores, and looks like we've got 1, 2, 3, 4, 5, 6, 7 different years. And does the ACT score depend on the year the tests were taken? So if I look at this 20.6 right here that I'm circling, is that number dependent on the fact that students took them in 2020? Absolutely. Is this 20.7, that overall score, is that score dependent on the fact that those students took it in 2019? Absolutely. These scores are dependent on the year the tests were taken. And so we would say one depends on the other. Is the ACT score a function of the year? Most certainly is. Okay, and so I'm hoping you see just conceptually what it means for one depend on the other, but also mathematically, notice each x only makes one y. You know, in 2014, there's only one score that is produced. In 2015, there's only one score that's produced, et cetera, et cetera. Each x can produce only one y. So you cannot repeat the x's. And I would ask you this, do you think you can repeat the y's? And yeah, you can. In fact, you kind of see that here. A couple of different ways that the y values are repeating. So you can have a repetition of y values, and the set of ordered pairs would be a function. It's all based on the fact that that y value is dependent on that x value. That x produced that y. All right, very good. So now that we have the idea, the notion of dependence taken care of, now let's get into a little bit more of the algebra behind it. So obviously a variety of things I talk about during these lessons, a variety of things I write down during these lessons. I put this one in bold. Honestly, it's like such a simple statement, but I feel like it's probably one of the most important statements of the entire semester. It's that straightforward, though. A function, very simply, is just a set of rules that tells us what to do to the input. So we're going to talk a lot about inputs and outputs and what that means. So very simply, I'll read it one more time and then we'll do the flow chart. A function is a set of rules that tells us what to do to the input. So meaning, we start with an input, and the most generic input that we'll use is x. So if you can go ahead and just put x and then a little input underneath. And maybe you've seen this in your prior math classes, but that x goes through a little function machine. And I can't draw to save my life here, but this is my sad excuse for a function machine, and we'll call it function f. So very simply, that input goes through this function machine. And this function tells us what to do to the input. It manipulates the input. And when it manipulates the input, it produces an output. And you've seen this notation before. This would be the function value at x, which represents the output of the function. So again, we start with an input, goes through the function machine, The function machine tells us what to do to that input, and after it manipulates it, out comes the output. Input, output. Okay, good. So keeping this idea in mind, no math for example 1, but just very straightforward stuff. These are some simple functions to work with. I have function f right here and function g, and all I want you to do is tell me like what you would do to the input to get the output. Alrighty, so f of x equals 2x plus 1. So here's our input, and if I have an input, what I would do for the input, algebraically of course, following order of operations, is I would multiply the input by 2. That would be my first step. So I'm going to write that here. Whatever the input is, could be anything, could be x, could be a number, could be a symbol, could be anything. But the first thing I would do to that input is I would multiply it by 2, and after I multiply it by 2, I would then add 1. So whatever the input is, you're going to multiply the input by 2, then you're going to add 1. And after you do that, you get a final product, and that final product would represent the output of the function. Cool, letter B. Function g here, whatever the input is, what would I do with it? Well, the first thing I would do following the order of operations is I would square the inputs, and then I would subtract the input. So whatever that input may be, again, could be a number, could be an expression, could be a symbol, could be a variety of different things. It doesn't matter. As long as you know what to do to the input to produce the output, you can get the result. So I would square the input first, and then I would subtract the input. And whatever I get as a final product, again, represents the output. Okay, nice. Now let's get into example 2 and get a little more concrete with our algebra. So I've got a function, f of x equals x squared minus 2x plus 3. This function is in the quadratic family of functions. And if I know what to do, then all this stuff will hopefully start to speak for itself. So first things first, whatever the input is, I can look at this and say I will square the input, then I will subtract 2 times the input, and then I will add 3. So again, whatever the input is, I'll square it first, I'll subtract 2 times the input, and then I'll add 3 at the end. And then I'll get an answer. All right, well, let's go get them. F of negative 3, just starting it out. So inside the parentheses, now notice this is what is going to replace the x. This is our new input, everybody. And if it's our new input, it replaces the generic input of x in order for us to get an output. So I did this right here. We're going to do kind of a one or the other situation so you can really see the differences, and you should be able to over the course of this entire example. So input or output change, that negative 3 represents the new input of the function. Okay, and so what it means, and I'm going to try to be as clear and specific as possible with this, when I say f of negative 3, that negative 3 now replaces the generic input of x. So remember, I square the input, so I square negative 3. I subtract 2 times the input, so minus 2 times negative 3. And then I add 3. So this is the function machine, essentially, telling us how to manipulate the input. So that's where I am, right here. And then I evaluate it. And I'm going to go ahead and do that relatively fast for us. And so I get, the negative 3 squared minus 2 times negative 3. So it looks like I get 9 plus a 6 plus a 3. And again, I don't want to overstep here, but it looks like I would get 18. So negative 3 is the input. 18 is the output. Negative 3 goes in. The function tells you what to do to it. 18 becomes the output. Okay, great. Let's go on to the next. Oh, and by the way, let's kind of box these up. I like that idea for these in particular, so you have those answers readily accessible. All right, letter B, f of 2x. So do you notice the 2x inside the parentheses there? That represents the new input to the function. So if I know as 2x is going to be the input, then I'm going to perform the function rules on 2x. So what that tells me, knowing what to do, is square the input, and this is where you'd have to be a little careful, So square 2x, and then minus 2 times the input, and then add 3. So I'm really hoping you see that idea of when it's an input, as long as I know what to do to the input, no matter what the input is, I should be able to manipulate it appropriately. And guys, we've seen this before, of course. This is a product raised to a power. When I do remove the parentheses, and I'm going to go ahead and box this up momentarily. When I remove the parentheses here, I do 2 squared and x squared, so that would be 4x squared, minus 2 times 2x, so that would be 4x, and then plus 3. There you go. All right. Now I've been talking a lot about input changes, but I want you to take a look at letter C here. If you notice, inside the parentheses is still x. There's no input change. It's still f of just x. But what I am doing is taking f of x, taking the output, right? F of x represents the output. And what am I doing to the output? What am I doing to f of x? I'm just multiplying it by 2. So first order of business is to realize, oh, that's what's called an output change. Okay? Input is staying the same. I take my f of x, and I'm going to multiply it by 2. So in this particular case, 2 f of x. Well, if I look at this, this is f of x. Let me see it circled right here. Everyone kind of see that? That is f of x. And all I'm doing to that entire thing, as it says in the notation, is I'm just multiplying it by 2. So I'm doing 2 times the x squared minus 2x plus 3. I'm essentially performing the operation on the entire function. And so when I do that here, and hopefully you have enough room to kind of write all this down, I get 2x squared minus the 4x and plus 6. So when you work with these output changes in particular, please do make sure that you put it in standard form, which would be this right here. Okay, very good. Going to move on to the next one. And by the way, just for my purposes, I'm going to go ahead and just write the function here. I think I'll do it right up here, just so I don't have to go back and forth. But so the function was x squared minus 2x plus 3. Okay, if you feel like that's appropriate for you, so be it, but no worries either way. Okay, first of all, x plus 1 there. Notice it's inside the parentheses, and so that represents our new input. Excellent. So what does that look like? Well, as an algebraic expression, that is the new input. I'm going to go ahead and put that in. So remember, as long as I know what a function is supposed to do to the inputs, square the input, subtract 2 times the input, and then add 3. So that's exactly what I'm going to do here, everybody. I'm going to square the input. The input is x plus 1. I'm going to square it. Then I'm going to subtract 2 times the input. So that would be minus 2 times x plus 1, and then, of course, plus 3. Now, I'm going to do this in 2 steps just so you have it on your paper and it's feeling good. But basically, you know, order of operations. Don't forget, everybody, you cannot just do x squared and 1 squared and call it a day on that. X plus 1 squared means times itself. So x plus 1 times x plus 1 means you would FOIL it. So as I do this, f of x plus 1, if I FOIL that, I get x squared plus 2x plus 1. Distribute the negative 2 in, minus 2x minus 2, and add the 3. And of course, when I go ahead and clean things up to put this in standard form, I get, it looks like an x squared. Looks like these 2x's are going to cancel, and combine the units together, and looks like I get plus 2. All right, there you go. Good one. Now I'm going to do the best I can to not run out of room. Hopefully you'll be able to pull this off as well. Let's go into letter E. So f of x and then plus 1. Have I changed the input at all? No, it's still x there. So now I'm getting f of x, and then I'm changing that by adding 1. So notice the difference here, the plus 1 inside the parentheses versus outside. So of course this is an output change. Well, what does it mean to be an output change? Let's see if I can fit it in here. It just means I'm going to take f of x, which is that whole thing. And watch how nice and easy this is. Just going to take it. And I'm going to add 1. There you go. And let's go ahead and get an answer on this. So f of x and then plus 1. I get x squared. I get my minus 2x. And how about just plus 4 for good measure there. All right. So I'm hoping you're really starting to see the distinction between input change and output change. Notice I'm just trying to keep the numbers the same so you can really see it. Plus 1 inside, plus 1 outside. All right, how about this one? F of negative x. Do you see that that negative x has changed? It was x, now it's negative x. So it is an input change inside the parentheses. Well, what does that mean for us? When I do f of negative x, it means that's my new input. So I'm supposed to square my input. So that's exactly what I'm going to do. I'm supposed to subtract 2 times my input. And then I'm supposed to add 3. So as long as I know what the function rules are telling me to do, then I can just do that on whatever input is provided. So square the input, subtract 2 times the input, and then add 3. Now this one you're just going to have to be a little careful on, just a touch. This is actually product raised to a power, and you do have to remove the parentheses here. This is a big one, everybody, so focus on this piece. Think of this as like a negative 1x. And when you square negative 1, you get 1. And then when you square x, you get x squared. So when you remove the parentheses on this, and again, you will be doing this quite a bit, you get x squared, because negative 1 squared is actually positive 1. And then negative 2 times negative x is plus 2x, and then plus 3. So please do make sure you're able to see that okay. Last one in this problem set. Is this an input or output change? Again, nothing changed in the input, but it looks like f of x has changed by throwing the negative out in front. And so output. And so let's go ahead and do this last one here, and then we'll write a couple things in place so we're sure we know what to do. So negative f of x, well again, it just says take the negative of f of x. Well, here is f of x. So I'm just going to take the negative of that. And so that's what it would look like. And let's box up this last one here. So now this would be negative 1 times x squared. So this actually does have the negative out in front because you square x and you get that. Then you multiply it by negative 1, so it produces that right there. And then the negative distributes in, negative 2x. And, I'm sorry, it looks like I made just a slight mistake on that. Let me quickly rectify it right in there. So the original function, of course, had minus 2x. I'm sure you caught that. And so this would change it to a plus 2x right here. Okay, perfect. Crisis averted. Love when that happens. All right, cool. So now we really have made the true distinction between input changes and output changes. Let's draw just a quick conclusion right here and move on to our very next piece. So what does happen with an input change? Like, what did we do each and every time? And here's how I summed it up on my paper. I hope you would agree that this is the case. But in essence, we just replaced all of the x's, all of the inputs, all of the generic inputs of x. So we replaced all of the x values with the term inside the parentheses. Let me write that just a touch better. So with the term inside the parentheses. And you could see that here. I just replaced the x's with x plus 1. Here, I replaced the x's with negative x. All right, with an output change, and I think the output changes tend to be a little cleaner, but very simply, you perform the operation on the entire function. And I hope you would agree with this conclusion based on what we did in the previous example. Okay, so output change, all right. If I'm adding 1, just adding 1 to the whole function. That's it. Awesome. So that was a really good just equation problem using the notation to manipulate the equation form of the function. Now let's move into more of a graphical function. Again, really emphasizing the concept of inputs and outputs, and just making sure we remember a couple things, because as I said, you've seen this before for sure. So example 3, use the graph to answer the following questions. And so here's my graph over here, and this is just meant to be a refresher. So you do know this. You've seen this idea before. When we look at a graph, we should be able to look at it right away and determine whether or not it represents a function. So it says, how can we tell if it does represent a function? And it comes from what is called the vertical line test. Again, that shouldn't be a new phrase for you. I will quickly summarize the vertical line test. So the vertical line test is essentially this. If you can draw a vertical line anywhere on the coordinate plane and it touches more than 1 point, then it is not a function. Okay, so I'll repeat that one more time. If you can draw a vertical line anywhere on the coordinate plane and it touches the graph at more than 1 point, then it is not a function. So in this particular case, does this graph represent a function? I would absolutely positively say yes, it does. And because no matter where I draw a vertical line, anywhere at all on the coordinate plane, I can never get it to touch the graph in more than 1 point. It intersects it here just at 1 point, at 1 point, at 1 point, at no points. Okay, so again, you've seen that before. I hope I summarized that okay for you. And it does gel very nicely with, if you remember the definition at the very beginning of the lesson. So for example, don't do this on your paper at all. I just want to be super quick with this. But what if the graph continued to like go down here or something like that? Then you could see that, oh, wait a minute. Then the graph would be touching here and here. Oh, now it touches more than one spot. And so the graph would not represent a function if that was the case. So you can see what would represent a situation where it would not be a function. That would not pass the vertical line test. And by the way, if you remember, let me just be super fast here. If I go back to my very first board, no repeat of the x values. We'll look at the vertical line test here. If you look, see this x value would be -3, so this would be -3 comma something. It looks like 0, of course. And right here, that also would be -3 and something else. And so you have an x value producing 2 different y values. And obviously, as we talked about, that cannot happen. So erase all that if you would. Vertical line test holds. Okay, perfect. Let's use the graph here. Find f of -2. Is -2 an input or an output? Hopefully at this stage you're starting to see that that is an input. If it is an input, that -2 represents the x value. Inputs are the x values. So what I want you to do is on the graph, find where you have an x value of -2. So I'm tracing the graph, looking at it pretty nicely here, and I notice, oh, an x value of -2 would be right there. Well, what is the y value? What would be the output for that particular input? And I hope you see that it's +2. So that is the y value right there. Input, output. Letter C, determine the value or values of x to satisfy the equation f of x equals 0. Is that 0, is that an input or an output? Notice it's f of x equals 0, so this is an output, meaning it's a y value. So find a y value of 0. I see 1 here. I see 1 here. What are the inputs that produce them? Well, in this particular case, it looks like -3. So I would say f of -3 equals 0. Input, output. And I see this one. Input is 5. Output is 0. Cool. So do want you to be really clear on input versus output. And remember, at the end of the day, and this is why I put it up here, when you see f of x, it's really just a fancy way to talk about y. So I'm going to write it like this. F of x is just an alternative way to write y. That's it. When you see f of x, that's y. So y value of 0. Okay, we're going to do a lot of association verbally over these next many lessons here dealing with functions. So the second investigation is just getting comfortable with some of the vocabulary. I've already used some of it today. So it just says draw a vertical line down the middle, associate one set of vocabulary words on the left and the other on the right. All right, I'm going to be quick here just to show you what I'm looking for. Inputs on one, outputs on the other. You'll hear me use those words a lot over the course of these lessons. Input, output. Now when I talk about the inputs, everybody, as I've been alluding to over the course of this lesson, inputs are the x's, outputs are the y's or the f of x's. Okay, again, when I hear inputs, I think about x. When I hear outputs, I think about y. We haven't referred to these two words just yet, but you've seen them before. Domain represents all the x values. Range represents all the y values. When we talk about application problems, we're relating two variable quantities. Independent variable represents x. Dependent variable represents y. Y depends on x. Dependent is y, independent is x. And when we start talking graphically, horizontal coordinates are x. I'm going to just shorthand that. Vertical coordinates are y. Okay. Awesome. I'm going to stop it right there. So again, just get a little practice dealing with the manipulation in the equations, understand graphically what it means to be a function, and how to look at it and analyze it and so forth. Thanks, everybody.